So far, every system we have modeled has been linear and time invariant. We wrote equations like x dot equals ax plus bu, where a and b are constant matrices. But most real-world systems are not linear. Springs stiffen, aerodynamic drag is proportional to velocity squared, and magnetic forces depend on both current and distance in a nonlinear way. In this lesson, we introduce the general nonlinear state space model and apply it to a magnetic suspension system. Let us compare the two forms side by side. The LTI model is x dot equals ax plus bu and y equals c transpose x plus du. Everything is linear in the state x and input u. The nonlinear model replaces these with x dot equals f of x and u and y equals h of x and u. Here, f and h can be any nonlinear functions. The matrices A, B, C, and D are gone. Instead, the system behavior is described by these general functions. This is much more flexible, but also much harder to analyze. As our example, consider a magnetic suspension system. An electromagnet is mounted at the top. Below it, an iron sphere floats in midair, held up by the magnetic force. A distance sensor at the bottom measures the sphere's position. The input is the voltage applied to the electromagnet coil. The output is the sphere's position. Our goal is to write the nonlinear state equations for this system. Let us draw the forces. The sphere has mass m. Gravity pulls it downward with force mg. The electromagnet pulls it upward with a magnetic force that depends on both the coil current I and the distance x. This magnetic force is given by c times I squared divided by x squared, where c is a constant determined by the coil geometry. Newton's second law gives us mx double dot equals mg minus ci squared over x squared. Notice that this equation is nonlinear because of the I squared and x squared terms. We define three state variables. x1 is the position of the sphere, measured downward from the electromagnet. x2 is the velocity, which is x1 dot. x3 is the current through the coil. For the electrical subsystem, the coil has resistance R and inductance L. Applying Kirchhoff's voltage law, L times the derivative of I plus R times I equals U, the applied voltage. So x3 dot equals U minus R times x3, all divided by L. Putting it all together, we get the complete nonlinear state equations. x1 dot equals x2. x2 dot equals g minus c over m times x3 squared divided by x1 squared. x3 dot equals 1 over L times the quantity u minus r x3. The output equation is y equals x1, the sphere position. In vector form, x dot equals f of x comma u and y equals h of x comma u. The function f contains the nonlinear term x3 squared over x1 squared. This is what makes the system fundamentally nonlinear. Watch the simulation. When we increase the coil current, the magnetic force grows and pulls the sphere upward. When the current decreases, gravity wins and the sphere drops. The key insight is that the force depends on both current squared and position squared. At small gaps, even a small current creates a strong pull. At large gaps, you need much more current. This nonlinear coupling between position and current is what makes magnetic suspension control challenging. The nonlinear block diagram looks different from the LTI version. Instead of transfer function blocks and summing junctions, we have nonlinear function blocks. The input u enters the function f, which outputs the state derivatives. These pass through integrators to give the states x. The states then enter the output function h to produce y. Notice there are no transfer functions here. Transfer functions only exist for linear systems. For nonlinear systems, we must work directly with the state equations. To summarize, most real systems are nonlinear. The general nonlinear state space model is x dot equals f of x comma u and y equals h of x comma u. We modeled a magnetic suspension system with 3 states: position, velocity, and current. The nonlinear terms arise from the magnetic force equation, where force depends on I squared over x squared. Unlike LTI systems, nonlinear systems cannot be described by transfer functions. In the next lesson, we will learn set-point linearization, a technique to approximate nonlinear systems as LTI models near an operating point.